Alright, stop. Collaborate and listen. Ice is back with a brand new invention, something. Got a hold of me tightly, flow like a harpoon daily and nightly. Will I stop? I don't know. Turn off the lights and I'll glow. Welcome to Honors Physics Lesson 7.6, Part B. Alright, so in 7.6a, which hopefully you watched first because it's A and not B, we talked about power being the rate at which work is done, and we did a couple of quick practice problems. Now we got the doozy of a problem. Alright, so basically, A, B, C, and D, not too bad. E can be a whopper because we have that F word, which is friction. Oh my god. Alright, so let's focus on the first parts though, because you're going to need those anyway. So we have this object. It's 30 kilograms. So mass equals 30 kilograms. At first it's frictionless, so that's good. Our force equals 120 newtons, and our time equals 5 seconds. I'm sorry, I'm writing all over the place, but it seems to be easier that way for me, even if it's not for you. So, ha! There. Okay, anyway, so average power is going to be our work over time, or force times distance over time. So, we have our force, 120. We don't have our distance, but we have our time, which is 5 seconds. All right, so all we need to do, right, this is all we need to do in physics, right, is figure out this delta x, which we should be able to do given our force and our mass. So if you remember way back when we dealt with Newton's second law alert, all forces equals a mass times an acceleration. All right, now be careful, because the acceleration is not the same as the acceleration of gravity. Gravity pulls down, and this is moving over, right? So it's not going to have an acceleration of 9.8. It's going to have an acceleration based on the force that's being applied to the horizontal, which is 120 newtons. So that 120 newtons equals 30 times A. So our acceleration should equal 4 meters per second squared. Alright, so I know what you're thinking. Whoopity-doo! I still don't have delta x. Well, if you remember way back when, again, even further back when, delta x equals 1/2 acceleration times squared plus DRT. Delta x, that's what I want! It starts at rest, so that means our velocity initial is 0. So we have 1/2 of 4, 5 squared, remember the time from before, 5, plus 0 times 5. So our delta x equals 50 meters. Now that I have this, I can plug it in over here to figure out our average power. So we have 120 times 50 divided by 5, and that should give us an average power of 1,200 watts. Alright, so for the whole thing, for the whole travel, for that whole 5 seconds, you're averaging 1,200 watts. So we don't have a lot of power in the beginning, we have a lot at the end, that's our average. Sweet. B and C are very similar, so what we're going to do is we're going to find our instantaneous power for 2 seconds and for 4 seconds. So instantaneous power instant. It's like an instant pot. Alright, anyways. 120 times V. I don't know V! That's alright. We can find V, right? Because, side note, our acceleration that we found before is our change in velocity over time. We got the time. 2 seconds and 4 seconds. So let's do that for both parts. So this is B and C. So for B, 4 equals change in velocity over 2. For C, 4 equals change in velocity over 1. Yay! Look at that, right? 2 seconds and 4 seconds. So cool! Okay, so for part B, we'll do that, keep that in red. We have 120 times our velocity. Well, 2 times 4 is 8. So for part B, we get 960 watts. But that's not 1200! Right, so this is instantaneous power. So at 2 seconds, we only made this amount of power. Aww. But for part C, we have 120, which is our force, times 16 meters per second. And that'll give us 1,920 watts. Yay, that's more power. Alright, cool. So, why is there a difference? Why is the power increasing? Right? Why is the power increasing? So, as you are applying this force, it's a contact force. So the longer you push, the faster it goes. Since work is dependent on your change in kinetic energy, you have more velocity, more work is being done. Cool. Awesome. Let's go and talk about part E, because now we're going to exert this force at an angle of 60 degrees below the horizontal. So we're doing part I, which is figure out the average power generated by friction if the coefficient of friction is 0.1. All right, so do this in this is all part E. All right, so part E. A coefficient of kinetic friction is 0.1. We are at an angle which is 60 degrees. So if we look at our object here, we are applying this 120 newtons below the horizontal. So this dashed line represents the horizontal. We are pushing down that way with 120 newtons, which means that not only do we have the force of gravity going down, we also have our applied force. Right? So in order for this object to not fall through the ground has to push with a force that is greater than force of gravity and the force applied. So that means that our normal force should equal the force of gravity that's positive plus the force that we are applying, but only in the y direction. So we need to figure out that component right there. So if this is our angle right here, then this should be the opposite side. So the y component should equal 120 newtons times the sine of 60 degrees. So that should be 103.9 newtons. All right, so why do I have to do all that? Well, the force of friction should equal the coefficient of friction, kinetic, times the normal force. So I need to know what the normal force is. So our normal force should be the force of gravity, which should equal our mass, 30 times 9.8. Forgot if it was 30 or 35. Alright, so normal force equals 103.9 plus 294. So 397.9. And that's because we are pushing down. If we were lifting up, so if this angle is above the horizontal, we would not be adding to friction, we would be reducing friction. Right? So think about when you're pushing something, if you push down, it's harder than if you lift up a little bit and pull. All right, so force of friction, 0.1 times 397.9. So that equals 39.8 newtons. All right, so friction going that way, 39.8 newtons. All right, cool. So remember, we're looking for the power that is being generated by friction, or the average power. So now we have the force, we need to know the distance. Unfortunately, it's not the same distance as it was before. Son of a nutcracker. Because all this 120 newtons isn't being applied to the x component now, because now we're below the horizontal. So we need to figure out our distance, which means we need to figure out our acceleration, which means we need to know how much we are pushing in the x direction. So the x component should be the cosine of 60 times 120. So 60 newtons. All right. So to figure out our new acceleration, we're going to take that 60 newtons divided by our mass, which is still 30, and that'll give us a new acceleration, which is equal to 2 meters per second squared. Notice that it's lower because of friction. All right, so unfortunately, we have friction going on. So that's going to be taken away from this acceleration. So there's two ways that you can look at it. You can look at it as if this acceleration is not your net, but is just the acceleration that we're getting from the force applied. And then you can look at friction as having its own acceleration, which works, but there's only really one net acceleration. So I would try to avoid this if you can. It still works, but what would be better is if you figure out the force net. So force net should be all of our forces added together. So 39.8 in the opposite direction plus 60. And that will give us a net force of 20.2 newtons. If we divide that by 30, that'll give us a net acceleration of 0.67 meters per second squared. Now we can figure out our delta x. The same way we did before. Delta x equals 1/2 0.67. It's still doing it for the same. So 5 squared plus 0 times 5. So our delta x should be much smaller. It's only 8.42 meters. All right, so work done by friction. All the way back to the beginning. Boop. That's going to be 8.42 times the force of friction, 39.8, divided by the time that it does it, which is 5. And our power generated by friction, or average power, to be 67 watts. All right, cool. I will save the last one for you since I've been going way over with time. It's going to take forever to upload this to YouTube. Just keep in mind all the stuff is the same with the exception of one thing. The exception of one thing, and that is instead of being above the horizontal or below the horizontal, we're going to be above the horizontal. So instead of adding our applied force like we did here, we're going to subtract, right? Because we're lifting up, so that should reduce the amount of friction. Okay, I will see you next time. Same bat channel, same bat place.